Good morning, everyone. I hope you all had a really nice weekend. Thank you for joining us for our first live group tutorial of the day and of the week. As you know, this is a GCSE Chemistry session, and the topic this morning is rates of reactions and collision theory. If you've joined us before, welcome back to our live group tutorials. But if this is your first time, we'll just give a quick overview of how this will work. So this will be an hour-long session led by our tutor, and so it will finish at around 11:15. Any questions you have throughout, you're able to ask via the chat or the Q&A, and we'll keep an eye on those questions and answer them as we go along, and then have some time for a short Q&A at the end of the session if we've missed any questions. So that's a chance for you guys to be really interactive, answer any questions, and ask any questions you might have as well. And just a reminder that all of these sessions are recorded. So if this is your first time and you wanted to go back and watch any of our past GCSE Chemistry sessions, you can do so on the My Tutor YouTube channel, which has all of our past tutorials as well as some shorter videos related to all the topics that have been covered so far over the past few weeks. So I'm Tilly, I work at My Tutor. Let me know if you have any questions about the online school. And our tutor for GCSE Chemistry, as usual, is the wonderful Aman, who lots of you know, who's been teaching all of our GCSE Chemistry sessions so far. Aman studies medicine at King's and has completed over 150 lessons with us, so you're in really good hands this morning. Just bear with as we wait for a few more people to join. I think a couple of people were waiting to join. Someone's just asked, is the biology going to be more focused on foundation or higher today? So the biology session this afternoon, it's at 3:15. So I believe that that's going to cover a range of levels, but it's not specifically a foundation session. So it'll probably cover from around level 5 up to sort of the highest level. So not just foundation. Cool. If you're ready to go, Aman, let's get started.
All right, thank you, Tilly. Welcome back, everyone. I hope you all had a lovely weekend. And as Tilly said, today we'll be doing rates of reactions and collision theory. So specifically, we'll be looking at knowing what the rate of a reaction is and how to calculate the rate of reaction. We need to know that there are two factors in terms of particles that increase the chance of a reaction occurring. And then we're going to try and explain the effect of an increased surface area on the rate of a reaction. But before we go into that, let's just do a quick recap of what we covered last week. So on Friday, we looked at the higher tier calculations of bond energies. So I thought, given that we didn't have much time to do many of these calculations on Friday, this is an exam question, so let's try and do this and make sure that everyone still understands this topic and is happy with it. So hopefully you remember that when we calculate bond energies, we calculate the total amount of energy in the reactants, and then we subtract the total amount of energy in the products. And remember that when we break bonds, we use energy, so it's an endothermic process. So essentially when we break the bonds in the reactants, which in this case is hydrogen and chlorine, it's an endothermic process. But then when we form the bonds in hydrogen chloride, it is an exothermic process, and so energy is released. Remember, we remembered that last week by saying endo means take in, exo means come out. So if we think about breaking bonds as taking energy in and making bonds as producing energy and therefore it being transferred out. So first of all, to calculate the amount of energy in the reactants, we need to know the bonds. So we know hydrogen only has one electron in its outer shell. And we know that hydrogen goes around as a gas, so it will be H2, and that's a gas. Same with chlorine, it also goes around as a pair and as a gas, like so. And then it's going to form hydrogen chloride, which we know hydrogen has one electron in its outer shell, and chlorine is in group 7 and therefore can accept one electron. So when they bond covalently, you form HCl. That's because hydrogen donates or shares its electron with chlorine, and chlorine shares its electron with hydrogen. So it's HCl. There's only one electron share going on there. So that's the formula, and then if we balance that out, we know there's 2 hydrogens and 2 chlorines on the reactant side. So to do that on the product side, we need to put a big 2 in front. So that's the balanced equation. Hydrogen plus chlorine goes to hydrogen chloride. And now if we think about the bonds, in hydrogen itself, we know it's a covalent molecule, and when hydrogen shares its electrons, there's one electron shared, like so, because they only have one electron in its outer shell. So it'll be one electron from the left-hand side hydrogen and one electron from the right-hand side. So it's a single covalent bond, and therefore the bond energy involved in breaking that is 436. So it's 436 in hydrogen. And then in chlorine, again, that's in group 7. So if it's in group 7, that means it has 7 electrons in its outer shell. It needs 1, so it's going to share 1 from each. So if we've got 1 coming from the left-hand side, that means it's got 6 left. And then 1 coming from the right-hand side. So again, it will have 6 left. And we can see that forms 8 in both. And so that is a single covalent bond. So the Cl-Cl bond will be 248. So the total amount of energy in the reactants is 436 plus 248. So 436 plus 248, which gives us an answer of 684. Excellent. The person that answered me, well done. So 684. So that is what goes into the endothermic process of breaking bonds. We're then going to subtract the amount of energy in producing bonds. So we need to know what type of bond HCl is. And again, we know hydrogen has 1 electron in its outer shell and chlorine needs 1. So it's going to be a single covalent bond again. So if we look on our table, HCl over here, single bond, that's what one line denotes, is 432. Therefore, there's 2 HCl's, so it will be 432 times by 4, which is 864. So we do 684 minus 864, and therefore we get a total energy, and we can see already that it's going to be negative. So you should get an answer of negative 180 kilojoules per mole. Does anyone remember what a negative bond energy means? Excellent to everyone that gave me answers, well done. Exothermic reaction, brilliant. So negative bond energy means it's exothermic. Really well done, everyone. Someone's just asked me, what does the double mean? So here, where we've got a C, double bond C, that means it's a double bond. If it's just a single line, it's a single bond. Remember, a double bond means that 2 electrons are shared per element. So in oxygen, for example, it shares 2 electrons. If you want to cover more on that, we did that last Friday. So let's go on to today's topics then. So the rates of reactions. So the rate of a reaction is how fast the reactants become products. So, and there are 2 ways that you can really calculate, or 3 ways that you can calculate the rate of a reaction. There are 2 main ways. The first is that we can look at the rate of products produced. And the second is we can look at the loss of reactants. So as we do a reaction, the reactants are going to get used up. And so we can look at the rate at which those reactants are used up. Similarly, products are formed as we do a reaction. So we can look at the rate at which products are formed. The third reaction that's on here is about decreasing light. Now, this is a special example. It's not really done that much. You might have done it at school. And usually what this is when we react 2 reactants together and form a product, if one is insoluble, remember insoluble means that it does not dissolve in water, then it will make that water almost go a murky or cloudy colour. And so what we can do is, as the products are formed, because the water will become more murky or more cloudy, there will be decreasing light that will pass through the solution. So again, you can measure the rate by looking at the decrease in light that goes through the solution. So when we start off, the water will be clear because there won't be any product. And so the light intensity that gets through will be really high. But as we form a lot more product, the water will become murky. And so we can look at, well, actually, the light intensity will decrease. And what is that decrease to calculate the rate? Well done. So now let's look at one of these reactions. So this is a reactant graph. And the one thing I want to point out when I show you these pictures is the graphs. So if we look at this graph over here, we can see that this is a mass loss graph. And specifically, it's the reactants that are being lost. In this equation, or this reaction, we've got hydrochloric acid reacting with marble chips. Does anyone know what marble chips are? Or what makes up marble chips? Any ideas? Someone's asking, do double bonds require more energy to be broken than single bonds? Yes, they do. That's why if you look on the table, often they will be more. Someone's saying marble chips are alkali. Not quite. It's not carbon dioxide. Any other guesses what marble chips are? Brilliant, someone said calcium carbonate. So marble chips are calcium carbonate. So this reaction of hydrochloric acid with calcium carbonate will produce carbon dioxide and calcium chloride and water. So what we can see here is that the gas is carbon dioxide that's given off, and as we react, the marble chips or the calcium carbonate will reduce. So on this graph, we can see we start off with a certain mass, and then that reduces over time. And that's what this mass loss curve is. And so what this brown writing is saying is that the initial gradient gives the initial speed of reaction. So we look at the gradient of a line to tell us what the rate of reaction is. I'm going to go more into that in just a second. So we've looked at now the reactant loss. Now let's look at product formed. So again, this is a very similar reaction, but instead of magnesium carbonate, we've got zinc reacting with hydrochloric acid to produce zinc chloride and hydrogen. And this time we're looking at the gas produced. So it's still a production graph, and you can see that the graph goes upwards this time. So if I go back to reactants, it goes down when reactants are being lost, but when products are being formed, it goes up, which makes sense because as products are being formed, there'll be more volume of gas produced. And that's what we're measuring using this gas syringe. So this is why we've got producing here, or production graph here, and a reactant loss graph here. Then the final equation was the one that I mentioned about light being transmitted. And I said at the beginning, there will be the most amount of light transmitted, but as our product gets formed that makes the water murky, less and less light will be transmitted. So we get a downwards graph, just like reactant loss. And in this equation, I've said it's silver nitrate and sodium chloride, which forms sodium nitrate and silver chloride. And silver chloride is insoluble, so it's going to make that water cloudy. Someone asks, does gas have a mass? You can't really measure the mass of a gas, so that's why they form the volume. So you always measure the volume of gas formed. If we were looking at a solid being produced, we would measure the mass of a solid, but with gases, we always measure the volume. So that's what a gas syringe does. So as more and more gas is formed, this syringe plunger will move further and further towards the right, and this will fill up with gas. So that's how we measure the mass, the volume of gas produced. Okay, so now that we know the three equations that look at rates of reactions, we actually need to know how do we calculate the rates. And there's two equations, and I'm sorry that it's not really projected very well on the screen, but essentially it's the amount of reactant used or the product formed, depending on what reaction we're doing. So remember, the first one I showed you was reactant being used and the graph goes down, and the second one I showed you was gas being produced and the graph went up. So you can do either of those, and then it's divided by the time. So it's nice and simple. We just start with the reactant used or the product formed over time. And if you're doing maths, hopefully you know what a gradient is. And basically the gradient says that the steeper that gradient is, or the steeper the line, the faster the reaction. So what that means is if on a graph our gradient is like this, whereas if it's like this, the faster reaction would be number 1, not number 2. And that's because this line is steeper than this. So this is a faster reaction, number 1 compared to number 2. And also the gradient at any time on the graph tells you the rate of reaction. Now we're going to do some questions to calculate the rates. One type of question is a higher tier question, so we'll have a go at a couple of those. The other questions are for both tiers. So the first thing we need to be able to do is calculate the rate of a reaction in a certain amount of time. And the second thing we need to be able to do, which is the higher tier question, is to calculate the rate at a specific time. So we'll go over both of these. Before we do that, which line here, number 1, number 2, or number 3, do you think has the fastest rate of reaction? 1, 2, or 3? Remember, we look at the gradient of the line to tell us. Okay, so everyone is saying 1. Excellent. So 1 has the fastest rate of reaction, and we can see that because this gradient is really, really steep. Another question, does anyone remember in maths how we calculate the gradient of the line? What's the equation for calculating the gradient of a line? Does anyone remember in maths? All right, brilliant. So we've got change in y over change in x, y2 minus y1 over x2 minus x1. Brilliant. It's exactly the same in chemistry. And for the higher tier questions, you need to know that equation. For the other tier questions, you don't need to know that equation, but it's good that we do know it. So let's start with this question here. The first thing, or the first question, is to calculate the average rate of reaction for the first 20 seconds in centimeters cubed per second. And this type of question is not a higher tier question, it's for both tiers. So to calculate the rate of reaction, remember I said it's either the reactants used or the product formed divided by time. And we can see this type of graph where it's going up is a product formed graph. And we can see that the volume of gas is being formed. So the gas is being formed and it's going up. If it was going down like this, that would be reactant being used. So they're the two types of graphs, and it's important that we can distinguish between those two. Brilliant. So let's have a go then. So in the first 20 seconds, what is the rate of reaction? So in the first 20 seconds, that's here, we need to know how much product was formed. So if we follow the graph up, we can see it's here, which is 30. So that means in the first 20 seconds, 30 centimeters cubed of gas was formed, and that was in 20 seconds. So to calculate the rate of reaction, it would be 30 divided by 20. And as someone has said, the answer there is what? Does anyone else know the answer? We've got one answer so far. What's the, so people are saying 1.5, brilliant. So just make sure you also have the units. So it would be 1.5 centimeters cubed per second. Okay, so that's how to calculate the rate of a reaction. And again, we'll just do another one of these to make it absolutely clear. If I now said to calculate the rate of reaction between 20 and 40 seconds, if we have a look at 20 seconds, we know it's at 30. At 40 seconds, we know it's at 50. So the volume of gas produced is 30. And again, if we divide by the time, it's 20. So again, the rate of reaction, because between 20 and 40 is 20 seconds, is 30 divided by 20, which is 1.5. So to calculate the rate of a reaction during a certain time period, you just look at the product formed or the reactant loss divided by the time. And that is in both tiers, foundation and higher tier. So the specific higher tier questions are to calculate the rate of a reaction at a specific time point. And this is where we need to be able to calculate the gradient. So it's quite difficult for me to do on the screen, but I'm going to have a go at trying to draw the gradient for you. So if we start off then, at 40 seconds, I need to draw a gradient. So you look at the 40-second line and you try and draw a straight line. So it will be something like that. Okay, so we draw a gradient, which is a straight line at 40 seconds. We then need to draw a triangle, which will help us to calculate the gradient. So to draw, when I look at that line, I can see a triangle, and the triangle I can see that's on nice coordinates is that triangle there. So what we can then see is we do the change in y. So the change in y is how far up it goes. So that's from 40 to 50, which is 10, divided by the change in x, which is 30 divided by 40, which is 10. So the gradient is y divided by x, which is just 1. So it's 1 centimeters cubed per second at 40 seconds. And we can see that it is starting to level off, so the rate of reaction is slowing a little bit from when we first calculated it. Let's have another go. So let's do the rate of reaction at 60 seconds. So again, we do a gradient at 60 seconds. So somewhere like that. Remember, it's got to go through 60 seconds as a straight line. It's not supposed to go through the curve when you do a gradient. As I said, though, it's quite difficult for me to do on the screen. So there we go. And again, we need to draw a nice triangle. If we can't see a nice triangle, try and at least make sure you're on the crosses. You don't want to be halfway in between the dots. So you can see that that is a coordinate there, and this is a coordinate. So if I do that, we can see we've gone up to 67 there, and the bottom coordinate is 60, so that's gone up 7 and along from 60 to 80, which is 20. So it's gone up 7 divided by 20. So change in y divided by change in x, and again we're expecting a massive decrease in the rate, so 7 divided by 20 will give you an answer of 0.35. So 0.35 centimeters cubed per second. Excellent. To everyone that gave me answers, really well done. Someone's asking, is this like doing a tangent in maths? Yes, it is. So it's exactly like doing a tangent. And that's why it's a higher tier question, because you're involving maths things as well. Really well done, everyone. Okay, let's do another question. So now this is a reactant loss graph. And again, the reason I can tell that is because the graph is going down. So remember I said you need to know two types of graph. That is product formed, reactant lost. All right, so that's formed and lost. So on this graph, we can see that this is reactant being lost. So we need to calculate the average rate in the first 400 minutes. So let's do that first. So again, this is not a higher tier question. This is just both tiers. So in the first 400 seconds, we can see that the product loss goes from 1.8 to 1.2. Therefore, that is 0.6. And it's in the amount of time of 400. So the answer to the first question, which is the average rate in the first 400 minutes, is 0.6 divided by 400. So what's the answer then? What's the rate in centimeters cubed or moles per minute? Anyone know? So we've got 0.6 divided by 400. What's the rate? Yep, brilliant. So someone's given me an answer of 0.0015. And what we can see is it's really important that you do read the question to see what kind of unit they want. And they've said they want it in moles per minute. So we can see that it's right. We don't need to change this into seconds. It is in moles and minutes. So yeah, 0.0015. Brilliant. Okay, so the next question then is to calculate the rate of reaction at 1,000 minutes. So 1,000 minutes. This is a higher tier question because we need to find the rate of reaction at a specific time point. So what's the first step that we need to do? Yeah, find the tangent. That's the first step. We need to find the tangent. Excellent. So I get my line out or my ruler out in the exam. You find where 1,000 is and you make sure that your line goes exactly through that 1,000 point. So something like that. Try and make it as long as possible because it will just help you to draw a nice triangle, but make sure it goes through that 1,000 point. Okay, then you're looking for what? What's the next thing you're going to do? So I draw my tangent. What's the next step? Any ideas? Draw a triangle. Excellent. So we need to try and find some nice coordinates to draw a triangle. So it's a bit difficult with this one. So I'd say there's a coordinate there and there's a coordinate here. Okay. So again, it's quite a small screen, so it's difficult to see. So going up then, we first need to calculate what the scale is. So does anyone know what this point is and what this point is? Anyone work that out? I'll try and make it a bit bigger. There you go. What's that point and what's that point? So what's the scale between 0.6 and 0.8? So hopefully you've worked out that there's 5 small squares between 0.6 and 0.8. So that means each one is worth 4. So the first one, as someone has said, is 0.68, which is excellent. Well done. So 0.68, and the second one is 0.88. So again, to work out the scale, if you look at the difference between the numbers, so for example, between 1.2 and 1, there is 0.2. And then if we look at the number of squares, there are 5 small squares between that. So if we do 0.2 divided by 5, that means each small square is worth 0.04. So yeah, going up, it's between 0.68 and 0.88, which is 0.2. So it's going up 0.2. And then going along, it goes from 800 to here. That one there. So again, if we look at the difference between, so it's 200 between 1200 and 400, there are 5 small squares, so that means each one is worth 40, so that would be 1280. Okay, so now we've got an up of 0.2, and a log of 1,280, we're just checking the question, it's moles over minutes. So again, we don't need to change it into seconds or anything. So what's 0.2 divided by 1,280? Any ideas? 0.2 divided by 1,280. You can give it to me in 3 significant figures. Oh, sorry, someone's saying, shouldn't we do it at 480? Yep, you're exactly correct. Sorry, that's my mistake. So a long goes from 800 to 1,280. So yeah, it's 480 a long. Sorry, I forgot to do the third step, which is calculates the change in x. So yeah, so 0.2 divided by 480. So if you can give it in 3 significant figures. Brilliant, so 0.00417 to 3 significant figures. Great. Okay, so before we move on, any questions on calculating the rate of reaction? So there's 2 types of questions. The first one is calculating the rate in a specific time period, which is just about finding how much product was formed or how much reactant was lost divided by time. And the second one was about how looking at a specific time point, which is a higher tier question, and then calculating the gradient as we do in maths. So any questions on those at all? Okay, before we move on to the next part, someone did ask me about the bond energy, so I just want to go back to this. So just to show you, this single bond OO has a bond energy of 145, whereas a double bond has 498. So when we have double bonds, often because they're more strongly bonded together, there's more energy that's needed to overcome those covalent bonds. So remember, when there are more electrons in there, there's stronger attraction between the electrons, and therefore more energy is required to overcome that bond. Okay, so the next thing then is going on to calculating the rates of a reaction in terms of collision theories. So collision theory is what we're going to be covering a lot of today and on Wednesday. And specifically, we're going to be looking at the factors that affect collision theory. So the one thing I want to look at first of all is what 2 factors are needed for collisions to take place. And the main thing is that the particles or the reactants need to have enough energy. So if you remember from last week, we looked at reaction profiles. And remember that reaction profiles look at exothermic and endothermic reactions. So for example, an exothermic reaction will start here and here, and it will go up like so. And that's an exothermic reaction where we've got a negative energy change between reactants and products. And what we can see there is that this here is what? Does anyone remember what this arrow here is? What does that arrow represent? So I'll draw it again as an endothermic reaction as well. So we've got reactants, products. What does this arrow here represent? Activation energy. Excellent, well done. So we went through that last week, if anyone's wondering. And it's really important that when reactions take place, the reactants need to have that activation energy for a reaction to take place. So the first thing that's really important is that if the reactant particles are going to have the activation energy, there's 2 things that need to happen. The first thing that will increase the chances of it is if they collide more frequently. So if they collide more frequently, the chances of the collision having enough energy increase. So if we've got more collisions, the chances of 1 or 2 of those collisions being enough of the activation energy increases. The second one is if they collide with more energy. So there's 2 factors. The first one, if they collide with more energy, and the second one, if they collide more frequently. So all of collision theory is based on those 2 things. So the frequency of collisions and the amount of energy in the collision. So for example, if we've got 10 particles in one space, there might be quite frequent collisions. Whereas if we've only got 5, there will be less collisions because there's less particles there, and therefore there's less chance of a collision occurring. So they're more frequent when there's 10. That's the first thing. The second thing is about the energy. So if we increase the temperature, for example, the particles will have more energy, and therefore they will collide more frequently. So we'll be looking at temperature tomorrow, but it's really important that we understand those 2 factors in determining the activation energy. So does anyone remember the definition of activation energy? Yeah, someone's asking me to explain the activation energy again. I will. Does anyone remember what the definition is? Brilliant. So someone has said the minimum amount of energy needed to start a reaction. So that's exactly what it is. And often before a reaction takes place, a lot of reactants need some energy in there to allow the reactant particles to react. So the activation energy is the minimum amount of energy. And often we don't want to put more than the minimum amount of energy because energy costs, and so it's a waste. And also when we use energy, we tend to burn fossil fuels, so it can pollute the environment as well. So that's why the minimum amount of energy is called the activation energy. We don't tend to put in more than that. But for a reaction to take place, the particles must have that minimum amount of energy. And therefore, when they do, in exothermic reactions, which is this graph here, the particles will lose energy because energy is being transferred to the surroundings. Remember, that's what exothermic means. So the products will have less energy because energy has gone into the surroundings. Whereas in endothermic reactions, the products have more energy than the reactants. Some is still lost because remember, when we put in the activation energy, the products aren't going to stay at that activation energy. They're going to lose a bit of energy, but it's still more than the products. So they're still taking in that energy from the atmosphere. So in endothermic reactions, the atmosphere or the environment becomes colder because the products take in that energy. Whereas in exothermic reactions, the atmosphere becomes warmer. So you may remember that last week when I looked at exothermic and endothermic reactions with you, I made two distinguishments between exothermic and endothermic reactions. The first is that in exothermic reactions, the products have a lower energy than the reactants, whereas in endothermic, so this is endo, this is exo, the products have more energy than the reactants. So that's the first difference. The second difference is about the temperature of the atmosphere. In exothermic reactions, energy is given out, so the atmosphere increases in temperature. In endothermic reactions, energy is taken in, so the atmosphere decreases in temperature. So they're the two differences between exo and endothermic reactions, and it's really important that we're clear on those. Okay, so let's go on to the one kind of factor that we're looking at today, which is surface area. So on the previous slide, I talked about the four things that we will look at, mainly tomorrow. So we're going to look at surface area today, but the other factors that we'll look at are temperature, the pressure of gases, and catalysts. So that will all be done tomorrow. Not tomorrow, sorry, Wednesday. So first of all, the surface area. So the larger the surface area, the more particles of reactant that are exposed, and therefore the faster the reaction. So let's look at that. So if you remember when we looked at nanoparticles a couple of weeks ago in structure and bonding, you may have remembered we looked at how nanoparticles have a larger surface area to volume ratio than normal particles. So let's use that concept now. So let's imagine we have a solid lump of, say, silver chloride, and that solid lump is a cube that measures 10 by 10 by 10. So if we look at the surface area of the cube, we said it's a cube that's 10 by 10 by 10. Remember, the surface area is the area of one face times the number of faces. So the area of one face is 100, which is 10 times 10. And the number of faces in a cube is 6. So it's 100 times 6. So the surface area is 600. And then the volume of the cube will be 10 times 10, so the surface area, times the depth, which is 10. So 10 times 10 times 10 is 1,000. So the surface area to volume ratio of our lump of silver chloride is 600 to 1,000. And remember, we always want to make it something to 1. So we can make it either 1 to something else, or so you can make the surface area 1, or you can make the volume 1. In this case, I'm going to make the surface area 1. So to make it 1, we divide by 600. So 600 divided by 600 is 1. And then we do 1,000 divided by 600, which gives us an answer of 1.667. So approximately 1.67. Then if we do the surface area to volume ratio of a smaller cube, so now let's think that we only have small particles or small cubes of silver chloride, which are 1 by 1 by 1. So 1 by 1 by 1. The surface area is 1 times 1, which is 1, times the number of bases, which is 6. And the volume is 1 times 1 times 1, which is 1. So that means if we look at the ratio of the surface area to the volume, this ratio is much smaller than this. So that therefore means that as we get smaller, the surface area to volume ratio increases. And that's why when we do reactions, often we tend to use smaller particles. So for example, using a powder rather than a solid lump, because it increases the speed of reaction. And the reason for that is that when there is more surface area to volume ratio, there is more surface area exposed. And so there are more reactant particles on the surface which can then react. Whereas when it's in a big, large lump, if you imagine there's lots of particles inside that big lump that can't actually reach the surface. Whereas when you've got a smaller cube or a smaller, finer granule like powder, all the reactant particles are pretty much on the surface and so can react a lot quicker. So remember the two factors that increase the chance of a reaction happening, and that is frequency of collisions and the amount of energy in a collision. With surface area, it's nothing to do with the amount of energy in the collisions. In fact, it's to do with the frequency of collisions. Because if there are more particles on the surface, that means that therefore there are more particles there in that surface area. Therefore, there are more frequent collisions that can occur. So in a large lump, there's less particles on the surface, and therefore the frequency of collisions is decreased. Whereas if we convert it to something like a powder or small granules, there will be more reactant particles on the surface, and therefore the frequency of collisions increases. And that's pretty much what the first 2 points says. And so the third point just says that the larger the surface area to volume ratio, the increased frequency of collisions. So does anyone have any questions about that before we watch a quick video to explain that? Any questions at all? Okay, so just as a recap, as we get smaller and smaller, the surface area to volume ratio increases, which means that there are more reactant particles on the surface, and because they're on the surface, that increases the frequency of collisions. So more collisions can take place as there are more particles there. Okay, so it's nothing to do with the energy. So remember, the two things that increase the chance of a reaction occurring are to do with the frequency of the collisions and the amount of energy. So it's nothing to do with energy. So surface area is all to do with frequency. So let's watch a quick video. Let me just, okay. So we've got 3 beakers here. And in this beaker, we saw what was in there. You can see that they're quite large lumps of calcium chloride, sorry, calcium carbonate. So these are marble chips reacting with hydrochloric acid. It's getting a bit smaller in the middle basin there, and then in the third basin, sorry, they're getting larger as we go along. So the smallest in the first one, in the middle one it's getting bigger, and in the third one it's the largest. So what are we expecting then? Which beaker, first, second or third, will have the fastest reaction? So the first one's got the smallest particles, the second one's got the medium, and the third one's got the largest. The first one, so we saw that there, so they've just turned, put the third one in, so we can see the reaction taking place. Now if we can see that reaction's taking place quite slowly. He's now done the second one. It's a bit quicker. So again, these particles are getting smaller. So these were the largest amounts of, so these were kind of pellets. We're becoming a little bit smaller. This is smallest. If we have a look, that is the fastest reaction. You can see all the effervescence there, so the bubbling going on and the gas produced. So what that was showing, I'll go back and show that again. So in the first basin, we've got the smallest, that's a powder. In the second basin, which he's about to show, so that's the first, so you can see the powder there. In the second basin, getting a bit bigger, they're a bit more like pellets or little tablets. And in the third basin, they're a lot larger, you can see that there. So as what happened, the first one, which has the powder in it, is the fastest rate of reaction because the reactant particles are all exposed on the surface, so the frequency of collisions increases. So now he's going to add the third one first, so the slowest one first. And there you go, you can see that the rate of reaction is quite slow. Just to say, it's not, so the mass will always stay the same. If we look at the second one there, the reaction's quite slow. Again, but it's faster than the first one. So you will always use the same mass of calcium carbonate and the same volume of hydrochloric acid. So you can see how fast that reaction is there. So the third one, or the first beaker, was the fastest reaction. Okay, so it's not the third one, it was the first beaker, so the one with the powder. So whenever you use something that's powder, it will always have a faster rate of reaction. And someone's asked me, are they all the same mass? As I said, you should, in an ideal reaction, you will have the same mass of calcium carbonate, but one will be in powder form, one will be in, tablet form, and then one will be in a large chunk. The hydrochloric acid should be the same concentration and volume. So remember, you always want your control variables and you only change one thing. So your independent variable should only be one thing, or what you change, it should only be one thing. And then in this case, we were measuring the reaction. What exam boards include this? So all exam boards look at rates of reactions. Someone's asking, why every time do I come in? I'm sorry, I don't know how to fix that bug. We can ask Tilly later. If powdered is even more, will the reaction will be even faster than the first one? Yep, so it wasn't quite a powder in the first one, but if it was ground into a powder, it would be even faster than the first reaction. So powder is kind of the smallest you can get reactants to be, so that will be the fastest reaction. So if you imagine the smaller something is, the more reactant particles that are exposed on the surface, and therefore the frequency of collisions increases. So let's do a question then. So in an investigation of the reaction between zinc and dilute sulfuric acid, a student compared the rates of reaction by measuring the time taken for a set volume of hydrogen gas to be given off. So what is formed when we react zinc and sulfuric acid? Does anyone know? Zinc and sulfuric acid. What do we think? So we've been told hydrogen gas. What's the other product? Zinc sulfate. Excellent. So it'll be zinc sulfate and hydrogen that's produced. So the student tested zinc powder and then zinc pellets of an equal mass. It was found that the powder gave off 25 centimeters cubed of hydrogen in 125 seconds, whereas the pellets took 235 seconds to collect the same volume of gas. Calculate the rates of reaction for both and explain the difference in terms of collision theory. So, can we calculate the rates of reaction for the powder and the pellets? So powder and pellets, and then we'll explain it using collision theory. So this is an exam question. It's an edXL exam question. So powder first. So the powder produced 25 centimeters cubed of hydrogen in 125 seconds. So what's the rate of reaction? Remember, the rate is either the reactant lost or the product formed divided by time. And you can give me the answer in centimeters cubed per second. So what's the rate of reaction for the powder? What do we think? So 25 centimeters cubed were formed in a time of 125 seconds. And the equation is how much is formed or how much is lost divided by time. Brilliant. So someone is telling me 0.2 centimeters cubed per second. So 0.2 centimeters cubed per second, which is exactly correct. So 25 divided by 125. Well done. Okay, what about the pellets? So the pellets also produced 25 centimeters cubed, but in a time of 235 seconds. So what is the answer to that one? So 25 in 235 seconds. You give me the answer to three significant figures. 0.106. Excellent. So 0.106. It's not seconds per cubic centimeters, it's cubic centimeters per second. So 0.16 cubic centimeters 0.106 cubic centimeters per second. So which one has the faster rate, powder or pellets? Which one has the faster rate? Brilliant, the powder. So the powder's got the faster rate. This is an exam style question, yes. It's an edX style exam question. So this is, so the powder has a faster rate, okay? So why? Using collision theory, why does the powder have a faster rate of reaction? Who can give me a nice exam style answer to that then? So we've gone through what an increase in surface area does. So why? Okay, so the first thing is that there's a larger surface area. What I am going to say is that in exam questions, they actually prefer it if you say there's a larger surface area to volume ratio, because that's actually more correct. Yes, it's got a larger surface area, but it's essentially, it's the largest surface area to volume ratio that's what matters. Sorry. Yeah, so a larger surface area ratio respective of the volume. Brilliant. So that will get you 1 mark. This would be a 3-mark question for the explaining in collision theory. Brilliant. So someone said a larger surface area to volume ratio. So there's a higher collision frequency and more successful collisions. Okay, almost. So I think the model answer would be that the powder has a higher surface area to volume ratio compared to the pellets, and therefore more reactant is exposed on the, or more reactant particles are exposed, and so there is a higher chance of collisions occurring, and you can put in brackets the frequency of collisions increases. And therefore this increases the chance of collisions being successful, and that just means having the minimum activation energy. Okay, so hopefully you can see that. So the powder has a higher surface area to volume ratio compared to the pellets, and therefore more reactant particles are exposed, and so there is a higher chance, sorry, that should say chance, and so there is a higher chance of collisions occurring. So the frequency of collisions increases, and therefore this increases the chance of collisions being successful. So that's kind of a model answer. It will give you 3 marks. So the 3 marks come from saying there's a higher surface area to volume ratio, therefore the frequency of collisions increases, and therefore this increases the chance of collisions being successful. Brilliant. So people that have given me the answer, well done. You're exactly correct. Someone's asking me, how does the powder react faster since the rate is 0.2, whereas the pellets is 0.106? Pellets are not smaller than powder. Powder is smaller than pellets. Powder's the smallest. 0.106, is that a faster rate, or is 0.2 a faster rate? If 0.2 is being produced per second, that is a faster rate than 0.106. Excellent. So someone has said 0.2. So 0.106 means that 0.106 cubic centimeters of hydrogen gas is produced per second, whereas 0.2 means that 0.2 centimeters cubed of hydrogen gas is being produced per second. So therefore, in the powder, there is more gas being produced per second, whereas in the pellets, there's less gas being produced. So the rate is faster for the powder versus the pellets. Would this come in a GCSE higher exam? So this is not a higher question. This is both tiers. It would be at the end of a foundation paper and probably about the middle of a higher paper. Collision theory is both a foundation and a higher tier topic. All right. Okay, any Q&A questions before we do a couple of exam questions then? So if you've got any Q&A questions, just pop them in the Q&A or the chat box and I'll try and answer them. And then we'll just do a couple of exam questions before we finish today. While I'm waiting for some Q&A questions, just as a recap of what we covered today. So we now know what the rate of a reaction is. It's how fast the reactants form the products. To calculate the rate of a reaction, we either look at the reactants lost, so the mass of reactants lost, which remember looks like this, or the products formed, which will always look like this. And by the way, when it levels off, that means we've formed the maximum amount in products, or in reactants, we've lost all the reactants. So when it levels off, the reaction has essentially finished. And to calculate that rate, we do the mass of reactant lost, or the volume or mass of product formed, divided by time. And it's usually in centimeters cubed per second if it's a gas, and it may be grams per second if it's a product which has a mass. The two factors in terms of particles that increase the chance of a reaction occurring and being successful is an increase in frequency of collisions and an increase in the amount of energy in the collision. And that therefore will increase the chance of a successful collision, which means that the collision has to have the activation energy. So remember, for reactants to occur, they have to have the activation energy, which is the minimum amount of energy for a reaction to occur. And then finally, we looked at surface area and what effect that has on the rate of reaction. And we said that as the surface area to volume ratio increases, so as something becomes smaller, essentially, more reactant particles are exposed on the surface, which means that there is an increase in frequency of collisions, which means there are more collisions, and therefore this increases the chance of a successful collision occurring and the reaction starting. So that's the four things that we've looked at today. I don't think there's any Q&A questions. As I said, if you have got any questions for me, just put them in the Q&A or the chat box function and I'll answer them. If not, let's do an exam question. So a student investigated the reaction of calcium carbonate, which is marble chips, and hydrochloric acid. The student recorded the volume of gas collected every 5 seconds. So what type of graph are we expecting if they looked at the volume of gas? Is that a reactant graph or a product graph? What type of graph are we expecting? Someone is asking me, how many marks would a question like this be? When you say question, do you mean the question I've got on the screen or the question that we just did about the pellets versus the powder? Brilliant, it's a product graph. So we are expecting something like this. So they recorded the volume of gas collected every 5 seconds. And they repeated the experiment using hydrochloric acid at different temperatures. We're not going to look at temperature changes today. We'll be looking at that tomorrow. And you can see the balanced equation there. And there we go. That is the graph there. You can see it. Someone's asking, it didn't cause any tutorials. I'm not sure.
Yeah, I'll just respond to that in a message because I think there's just some confusion over Zoom.
Okay, that's fine. Someone's asking me, do I recommend any good YouTube channels where we can find videos of experiments, as I find seeing them really helps me to understand? That's a really good question. I completely agree. I think videos are always helpful, and that's why I try to show them as well. Generally, what I do is just look at them in YouTube, and I just find I'll look at a couple of them and see if they're showing the same thing. I don't have a specific channel that I use, but Khan's Academy tend to explain things really well. The other thing that's quite good, I said this a couple of weeks ago, is BBC Bite Size. So they don't show videos, but they show kind of animated pictures, which are quite good as well. But for all the topics that I think need a video, I will always show a video. So tomorrow we'll be watching lots of videos for all the different factors that affect reactions. Okay. Brilliant. So state one conclusion that could be made about the effect of temperature on the rate of this reaction. So what happens to the rate? So remember, looking at the gradient then, which one's got a faster rate of reaction? And that's how we can answer that question. So someone has said, the hotter it is, the higher the temperature, and so the more efficient the reaction is. Brilliant. So we can see the 40-degree one has a higher rate of reaction, so it's going to be faster. So that would be the conclusion. And give one reason why the student could make this conclusion. What do we think? Why could they make that conclusion? Good, you can talk about the gradient being steeper. Brilliant, yeah, excellent. Okay, for the hydrochloric acid at 60 degrees, the student collected 30 centimeters cubed after 15 seconds. Calculate the average rate of reaction from 0 to 15. So what's the rate of reaction here? So the hydrochloric acid at 60 degrees, the student collected 30 centimeters cubed after 15 seconds. What is the rate of reaction? So I'll just wait for a few more answers, but I will say everyone that sent me an answer so far, you are correct. Well done. So good. So remember the units as well, centimeters cubed per second. They've given it to you in the question. If they didn't give it to you in the question, it would be a 2-mark question. But yeah, so remember to calculate the rate of reaction, it's the product formed, which in this case is the gas that's formed, or the reactant loss. There's no reactant loss in this question. It's product formed, which would be 30 over the time, which is 15. So 30 divided by 15 gives us an answer of 2 centimeters cubed per second. So well done to everyone that gave me that answer. That's excellent. It's not 1.5, it's 2. Okay. The student then investigated how the surface area of marble chips affected the rate of reaction. Which 2 variables should the student keep constant? So what do we think? So I kind of mentioned this when we watched the YouTube video. Which 2 variables do you think need to be kept constant? Yep, someone's asking me to go back to slide 10. Okay, so I'm not sure why we want to go back to slide 10, but I am going back to slide 10. So here's slide 10. Sorry to the people just answering that question. We'll go back to that in a second. I'm not sure someone wants to go back to slide 10. Okay, so we've gone back to slide 10. This was about calculating the rate. So just as a recap, to calculate the rate in a certain period of time, we look at the amount formed or the amount lost divided by time. But if it's at a certain time point, so this question here was asking at 1,000 seconds, you draw a tangent, and then you calculate the gradient by doing change in y divided by the change in x. So yeah, if we go back to this question then, so we've had a few kind of varied answers. What do we think? Which 2 variables should the student keep the same? If I go back to here, you can see which reaction they did. So they want to change the surface area. This is the reaction they've done. What do you think they need to keep the same? So have a look at that reaction. Now, if I go back, there's 2 correct answers. Okay, so we've had B and C. Yes, I agree. So it's not the amount of water because that doesn't matter. What does matter though is that we keep the concentration of acid the same. So if we do 3 experiments, and for example, the first experiment has powder, the second experiment has granules, and the third experiment just has a solid lump, we want the mass to stay the same. So if this is 3 grams, then this needs to be 3 grams and this needs to be 3 grams. It will just be in different size. So the size does not stay the same. The size is what's changing, but the mass stays the same. And the second thing is that the concentration needs to stay the same. So if we put it into, for example, 0.05 moles per decimeter cubed of hydrochloric acid, then they all need to put in to 0.05 moles per decimeter cubed of hydrochloric acid. The other one that would have been important that's not here is the volume of acid. That should also stay the same unless they're changing the concentration. But the volume should stay the same. And the volume of measuring cylinder doesn't make a difference because it doesn't matter. And the size of marble chips, I've said, will be changing. And as I said, the amount of water does not. Okay, so final question before we finish then. Explain in terms of particles and collisions the effect that increasing the surface area of marble chips has on the rate of reaction. So this is an AQA exam question for those wondering. So we did an edXL exam question before. This is an AQA exam question. So in terms of particles and collisions, so they've given you a clue there. So looking for 2 marks here. And there are 3 marks, kind of 3 points that you can make, but they're looking for 2. So any ideas? Otherwise, I'll write down a model answer before we finish. The higher the surface area to volume ratio, the more exposed particles. Good, the more particles, so a higher frequency of collisions will occur. Excellent. So, yep, your main points will come from saying the higher or the larger the surface area, I'm going to put larger. So the larger the surface area to volume ratio, and the more particles of reactant that are exposed, and therefore the more frequently collisions occur. And then you can say that increases the chance of a successful collision. Okay, sorry, that's a bit small. Let me make that a bit larger. There you go. So that's the answer to that question there. So the larger the surface area to volume ratio, the more particles of reactant that are exposed, and therefore the more frequently collisions occur, and that increases the chance of a successful collision. So really good work today, everyone. So tomorrow we will be, Wednesday we'll be covering temperature, catalysts, and pressure, and we'll be also starting to look at equilibrium, which I know a couple of you were keen to look at last week, so we'll be doing equilibrium this week as well. All right, hopefully I'll see you again on Wednesday, and then on Thursday. Take care, everyone, and I hope you enjoyed your lesson. Bye.
Brilliant, thanks Aman. And just a reminder guys, if you want to join us for any other sessions, we have Foundation Maths coming up and Physics and Biology this afternoon. Otherwise, as Aman said, see you on Wednesday morning for our next chemistry session. Have a lovely rest of your day and see you all soon. Bye.